Good evening, everyone. Welcome to Ground Improvement class. This is week 4. This is a um, discussion come theory class. I think we wait some few minutes to join others, and we start very soon. Oh, thank you. Good evening, everyone. Welcome once again. Welcome to this Ground Improvement Week 4 lecture and discussion class. This is our fourth class. We already done three more lectures in this way in these previous weeks, and Today it is our fourth one, and I am discussing here the ground improvement week 4 lectures, which is conducted by Professor Dilip Kumar Boydya sir in NPTL, and discussing the whole week 4 uh, theories and problems in this session. So I think this is already 6:05, so we can start our session now. So, so, starting with my introduction, once again, good evening. My name is Rajat Boni. I am a PMRF research scholar at uh, IIT ISM Dhanbad, and I am get opportunity to study or to teach the ground improvement lectures through NPTL. Actually, this is one of the not teaching. Actually, it is one like a discussion session of ground improvement. Only about four, week wise. So I am under Professor Dilip Kumar Boydya sir. He is a well-known person. He already taught the ground improvement in NPTL through video lectures, and I am just uh, deliver some extra to understand this topic very well. So today we discuss the ground improvement lecture for module 4 and 5. Week in week we discuss with fourth week we discuss the module 4 and 5, the materials, and already actually I think already share with you my NPTEL team. I'm discussing only that PPT or NPTEL, and also I will I will do at the end some problems regarding this class, and also discuss the previous year assignment problem in this session, and also give the solution of this problem. And if time permits, I will try to discuss previous week's lectures, that is week one, week two, week three. If anyone have any problem on that, and also I will address, if time permits, I will address some questioning from you, if any doubt from you. So we start our mm, today's class. So I am sharing my video, and another thing is that the video is recorded, will recorded and is shared to you through YouTube channel, and the link will be shared by NPTEL team to you, and also whatever I am discussing this session, what are the materials I am discussing. All these material will be shared by Google Drive to you through NPTEL team. So no, don't worry about this. And one thing that my network is disturbed in between. So please stay on the line. If any thing that my sound is not clear, my video is not clear, please cooperate me or tell me about that. I will adjust, uh, and I am now sharing my presentation. So please stay on the line and sharing. Give me a few minutes. So I think my screen is visible to everyone and my sound also audible to everyone. I think so. So let's start our lectures. So welcome to the ground improvement class. This is module 4. We have already gone through the module 1, module 2 and module 3. In module 1 we discuss about the introduction about the ground improvement. In module 2 we discuss about the shallow compaction and module 3 we discuss about the dynamic uh, deep dynamic compaction. Now today we discuss about the rapid impact compaction. Actually, it is in rapid impact compaction. In actually, when we studied the shallow compaction, we see that we will saw that shallow compaction is limited to up to zero point 0.3 meter. Lift or improvement depth or is up to zero point 0.3 meter, and deep dynamic compaction. When we study that deep dynamic compaction, the improvement depth is in between 10 to 15 meter. But in between that, if we apply improvement in between them, then we use the rapid impact compression. It is quite similar to the deep dynamic compression, but it is very quick than the deep dynamic compression, and also it is environmental friendly. But the depth of improvement is less than the deep dynamic compression. So, start with the first point. It is said that it is an intermediate compaction method between conventional shallow compaction and deep dynamic compaction. So we already told that I already told that it is in between shallow and deep. That means the in shallow we improve the ground up to zero point 0.3 meter or zero point 0.5 meter. That is less than 1 meter, we say. But in deep dynamic, we densify or the densify uh, up to 10 meter or 50 meter. But in between that, we use the rapid impact compaction. Then it is repeatedly dropping in this rapid compression. Actually, we repeatedly dropping a hydraulic hammer mounted on excavator at a fast rate. That means if you see in this figure, it is the excavator. The figure, it is one of the excavator, and this excavator we attach one hydraulic hammer, which is repeatedly, very quickly impacting one point and compacted the ground below it. This hammer weight is in between 5 to 10 tons based on your suitability and based on your targeted value, what you need. And the drop of height is fixed. It is always 1.2 meter. So it is quite the drop of height is quite low or less if as compared to the deep dynamic compression. Where we can see that it is up to 10 to 40 meter in deep dynamic compression, and also the weight of hammer is also less in case of rapid impact. We see that in deep dynamic compression, the weight of the hammer, not actually it is temper. Weight of the temper is in between 40 to 10 to 40 tons. But in rapid impact compression test is in between 5 to 10 tons. So energy wise, it is less energy is given to the ground. A rapid impact compression, but deep dynamic compression, the energy given energy is very large. Then in the next point, it is said that the drop on a circular steel foot of a diameter 1 to 1.5 meter. That means when we apply, before we applying the hammering or tempering, we plate insert a plate above the ground, and we above this plate we impacting or apply our energy or hammer. So why it is needed? Actually, we uniformly the ground is not level. So when we apply some plates, the circular or steel plate, the steel plate actually distribute uniformly distribute the load or energy what I given through the hammering. So it is very suitable when we apply the circular steel plate. Then the machine is generated 60 to 40 to 60 blows per minute. So we can see that this technique are very fast. We when we apply in case of deep dynamic compaction, we actually blow or drop. It is take time about one drop. It take times 5 to 10 minutes for second drop. But in yeah, yes, rapid impact compression, the blow rate is very high. It is about 40 to 60 blow per minute. So it is very rapidly impacting or compacting on a single point, and through this energy is distributed over a point, and like that the ground is compacted. So also in this impacted energy and the blows are recorded by through a digital skin or machine which is attached to this excavator. So so we record the impact energy and foot penetration. Then the production rate is up to 500 meters per improvement area per day. That means by this rapid impact compression test, we actually cover up to 500 meters square per day. That is quite a very big area as compared to the deep dynamic compression and shallow compression. Because we actually we achieve our goal or targeted improvement through very rapidly. That means if one point it is blows are 40 to 60 blows per minute. So we can see that the blow rate is high. So the energy also is transfer is very high, and up to that much depth it is very quickly improved. So this method is very suitable when in terms of the cost when the construction time available construction time is very less to us. So then we can apply this type of test, that is rapid impact condition. Coming to the next slide, here we discuss about the suitability, application, and what are the advantage and disadvantage. So it is suitable for granular geomaterial. That means granular in the sense means portionless geomaterial like gravel, sand, steel, or uncontrolled field. And also sometimes industrial and mine waste used to minimize the collapsible potential of the loads. That means when we apply that test, that is rapid impact compression test, we actually stabilize the ground through the vibration. We rapidly impacting one point and generating the vibration in one point. Through vibration, actually what happen if there is any possibility to collapse the soil or potential present, like or in the case of loose soil, then this all after before the construction we already stabilize the ground by vibration through vibration. So further after the construction there is no possibility to generate any collapsible nature of soil. So for that this test is very suitable. And also this test is suitable when we actually improve the ground up to 6 meter deep. That means when our target is 6 meter, or we can say commonly say the 3 to 4 meter, then we can use this type of test. Very quickly it is done. So the construction time is reduced, and also the cost of construction also reduced due to by duration. Then the application, what are the application of this test? That means what are the benefits we get from this test? Uh, like others ground improvement technique, this test also increase the bearing capacity, stiffness of the geomaterial below the foundation. Also, this test is used to stabilize the floor, slab, tanks, highways, railways, parking lots, airport runways, and mitigating the liquefaction and reducing the waste volume and collapsing hole. Well, how it is mitigating liquefaction? Actually, when we applying the rapid impact test, it's actually generating the vibration. Due to this vibration, we develop when the soil is saturated, there is developed the excess pore water pressure. Due to this excess pore water pressure, the soil effective stress is reduced and soil is behave like liquid. So then, if we excess pore water pressure is seeping out, or we can say this expel out from this ground, and the ground is stabilized, and we already mitigate or stabilize the ground for further liquefaction. Then this method is also used in concrete ground for a larger lift up to 3 meter. We already said that this may up to 6 meter also, but it is compacted for very suitable for a granular field in a larger lift up to 3 meter. Coming to the next slide, it is discussed here the advantage and what are the disadvantages. In advantage, it is said that it is very fast and much control compared to the deep dynamic compression. Fast in the sense it is actually fast because we applying the energy very fast by 40 to 60 blows per minute. So it is very fast as compared to the deep. While it can take one blows and then another blows in between. Then we take 5 to 10 minutes to arrange this test again. Then it is march control way. Why it is march control way? The certain the arrangement or arrangement of this uh, instrument is very small. So and the impact point is fixed through a steel plate, and we impacting the energy up above this steel plate only. So we can already decide, and due to the drop of height is very less, we actually generating a specified point. The energy is transferring through a specified point. So this is that much we fixed point we transferring the energy. But in case of deep dynamic compression, the arrangement is required very large thing is required, and also the height of fall and weight is very large. So it is may not be possible the impact point where we was already defined. It is may not the same impact point for the next drop. So in this case, the rapid impact compression fulfill our requirement as it is fast and much control. Then it is induced the much smaller vibration than the dynamic compression. So due to this smaller vibration, because why it is smaller vibration, actually we use the small weight as compared to the deep dynamic compression, and also the drop of height is very less. But in repeated way, we apply the small energy so that energy is transferred, same type of energy is transferred to, up to this depth of improvement. So it is due to the applying the small energy, the induced vibration also small. Due to this small induced vibration, we can use this technique very close to the existing structure also. So there is very less harmful or hazardous when we apply this test very close to the structure. There is no risk of the damage of the structure is very less in case of rapid impact compaction. Also, it eliminates the risk of generating fly debris. How it is eliminates this risk? Actually, we applying the steel plate. Above the steel plate, we applying the hammering. Then, due to this hammering, whatever the debris is created, it is already below the steel plate. So there is no generating. That is not generating the flying debris. So, and this flying debris sometimes cause hazardous in surrounding area. So it eliminates this type of risk. And also we can detect the weak zone during the operation. How it will we detect it? When we applying the rapid impact test, it is after 2 3 blows or 10 blows, we already find that if the ground is very soft in nature, the ground is subsidized or subsidized in very quickly. So by this seeing this, we can easily understand this. Below this plate or impact point, the ground is very weak. So we can also detect this weak zone through this instrument. And also it is a better mobility. It has better mobility and works in areas with difficult access. That means because in it requires a small excavator and also requires small height and small weight. So the mobility of the instrument is very fast. So it is then the dynamic compaction. So this advantage then this is the advantage about the dynamic deep dynamic compaction. Now coming to the limitation. This only one limitation is here there, that is it require it improve up to small depth only then the deep dynamic compression. Deep dynamic compression, the depth of influence is about 10 to 15 meter, but in case of rapid impact compression, it is up to 6 meter. Why it is 6 meter? Because of less energy transfer and the less energy is delivered to this ground. So that's why it is required. So it is so the depth of improvement is smaller than the depth of deep dynamic compression. So coming to the next slide, we actually now we discuss about the design consideration. What are the different aspects regarding the designing the rapid impact test? First one here it is depth of improvement. Because the technique and procedure is different from the deep dynamic compaction, the rapid impact, the depth of improvement also the different from the if we get the same formula is not used, which is already used in deep dynamic compression. Because of it, the procedure, different procedure and different techniques or process is used to densify the soil in rapid impact center. But there is one or two guidelines to estimate the depth of improvement, which is given by Bray 2003 and Says 2006. So in the next, it is in the table. It is so that to find out the depth of improvement for different geomaterial, one table is given, and also there is shown the how much energy or applied energy is given to achieve that much of depth of improvement. So first one here is show that the loose building waste. In loose building waste, the applied energy is about 150 and depth of improvement is about 4. 4 in meter. All the units are in meter. So, and in ash field, the applied energy required to is 150 to improve the ground up to 3.5 meter. And then when we select the granular field, for granular field, same the applied energy is 150, but the depth of improvement is 4 meter. For sandy silt, you don't confuse about the sandy silt and sinty silt. Both are different from their nature. In sandy silt, it is required 80 applied energy is required 80 ton meter per meter square to improve the ground up to 2 meter. And in silty sand, it is required up to 190 ton meter per meter square to improve the ground up to 3 meter. So like that, by this table, what are the our targeted improved area for what type of geomaterial we decided, and then we that much of energy applied by weight and height drop of height to the ground. Moving to the next slide, it is another table is given, and it is given by 9 ton hammer. When we apply the hammer weight when 9 ton, this table is given. This data is coming out. So here it is based on the SPT value and also based on the depth of removal value. For sand, it is shown that when we apply the rapid impact compaction test, after the compaction, the SPT number increased to 20 to 30, and depth of improvement increased to 6 meter. For silty set, the SPT number is increased to 15 and depth of improvement is increased to up to 4.5 meter. And sandy silt is in between 10 to 15. SPT number and depth of improvement is in between 3.5 to 4.5 meter. And uncontrolled field, it is greater than 10 meter and depth of improvement is for SPT value and depth of improvement is in between 3 to 5 meter. So here one point it is given that for a typical impact spacing of 1.5 by 1.5 meter, 30 blows of 9-ton hammer with 1.2 meter drop height generate about the 150 ton meter per meter square applied energy. So these are the threshold value for a 9-ton hammer for, with a drop of height is 1.2 meter and for an area influence area of 1.5 meter by 1.5 meter and blows required 30 meter to generate the 150 ton meter per meter square applied energy. So by this for another soil we can also determine. Now coming to another design aspect that is pattern of impact point. So here we can apply three types of pattern. One is arc pattern, another one is square pattern, and last one is triangle pattern. Based on our suitability and access to the ground and availability of the ground. So first one here it is shown the arc pattern. So arc pattern, the primary impact point are arranged in the arc around the center, which is shown in the figure, and secondary impact points are arranged between the primary impact point. So what is primary impact point? What is secondary impact point? Primary impact point are that points when the we apply the repeat impact test first to the ground, and then the secondary impact point when we apply the second time or we apply the second pass to the ground. So here we can see that the pattern is like in arc shape like that. For every but one common center. For all the points have one common center in an arc shape. So like that we apply the rapid impact in this to this ground. In this square pattern, in this square pattern we arrange the ground in such a way that the spacing between the primary impact point is very larger than the secondary and tertiary point. So if you see that there is a square pattern is developed when you joining this line, one 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 one. So after that we apply the secondary pattern. So secondary pattern in between this primary pattern. So secondary points are generated like this. Then we apply tertiary points. So for tertiary point, it is in between the secondary impact point. So it is like that. So like that, one area A by we can say A by A meter is improved. Like that, another A by A area is improved. Like that, continuously we improving the ground till the area is covered. Then you can see this another type pattern. It is triangular pattern like that, and like that. So here is the one point is given here. It is said that no ionic price is needed in rapid impact compaction since the rapid impact compaction is similar to the ionic compaction with low energy and close spacing. However, for leveling purpose and densify geometry near the surface compaction by roller is often needed. That means it is said that no need here ionic pulse, which is needed in deep dynamic compression. In deep dynamic compression, the applied energy is very large and the spacing between this impact point is also large. So there is an one catalyst form which is quite deep above from the surrounding ground. So from that to level the ground, we need the iron pulse for the deep dynamic compression. But in case of rapid impact compression, we apply steel plate on the ground and then above the steel plate we apply the energy and the spacing between this energy sorry in this impact point is also less than the deep dive compression. So distribution of energy is quite uniform. So the ground depression is also quite uniform. But for leveling purpose or finished work or finishing the ground, we sometimes we use the surface compression to level the ground or to smoothing the ground. So here by this point it is clearly told that we don't need the ionic pass for rapid impact compression, which is needed in deep dynamic compression. Coming to the next slide, another design aspect is number of blow. We can find out by this equation, one equation given, which is already same as the deep dynamic compression. We already seen this type of this formula. By this formula, we easily find out the how many drops are needed for one impact point for particular type of applied energy. So it is given that to determine the number of drop, we actually need the what type of soil is needed. For what type of soil, how much energy is needed to develop this these targeted or these targeted improve depth. And by this and also we also considered the how much weight is used for this applied energy and how what is the height of fall. And also we consider about the equivalent influence area. That means by applying energy, how much area is covering. That means how much area is compacted by that much energy. So by this we can easily find out the how much drop is needed. How it is find out? That means if we applied energy equal to the number of drop height of into height of hammer and drop height and whole divided the influence area. Influence area is nothing but the spacing into square of the spacing. If we apply the square pattern. So it is by that we can easily find out the number of drop. It is seen that this number of drop for rapid impact compression test is in between up to 40 meter. That means it's blow up to 10 to 40 blows per minute. We can see that. We already discussed about that. So we easily understood or we easily shown that by this formula we can easily find out the uh, number of blows per minute like that or what are the blows for per impact point, how much blows are needed. So coming to the next, another design consideration is this groundwater. So groundwater also most important for the different types of ground improvement technique. Here also it is a governing factor because like deep dynamic compression, the groundwater is problematic and it is also like problematic to the rapid impact compression. It because when we applying the energy to the field, if the ground is saturated or if the ground water table is close to the ground, there may be the seeping out the water from the ground due to the applied energy or uh, vibration. So this may not suitable for the construction site. So we need to dewatering the ground before the applying the rapid impression test. But if the ground water table is far between the 1 meter depth, then this technique is quite suitable. So it is said that as the deep dive compression, a high degree of saturation geometry near the ground surface affect the rapid impact compression, and the depth of ground water table is at 1 meter is minimum requirement for the rapid impact compression. If the ground table is too close to the ground surface, denaturing or additional field it should be implemented prior to the compression to suitable for the construction requirement. Then coming to the next slide in module 4, lecture 17, here it is given that like like other environmental impact, uh, other deep dynamic combustion, here also we consider the environmental impact. That means we consider the vibration and noise. How much vibration is created or noise are created after during this rapid impact compression, whether it is suitable to the adjacent site or construction site or structure or not. But based on that, we conducted the rapid impact compression test. If the if it is exceeding, it is not fulfill our the requirement, then we terminate the rapid impact compression test. So it is actually how it is find out the environmental aspect based on vibration and noise. It is find out based on peak particle velocity. The peak particle velocity is generated when the vibration is created. So based on some empirical formula, we can find out or we can define the peak particle velocity. So here it is said that like deep dynamic compression, rapid impact compression on ground induce the environmental impact, mostly vibration and noise. This fact has to be considered in the selection of suitable ground improvement technique. A loose soil or field typically generated lower peak particle velocity. Peak particle velocity is measured the disturbance of the soil. That means it's measured indirectly the vibration of the soil. If the vibration is more, structure is damaged, will damage, so the station will not suitable for that near area, and we rejected or terminated them. So how we can find out? There is given one formula, empirical formula to find out the peak particle velocity. So to find out the peak particle velocity, we need the scale energy factor. How it is find out? The scale energy factor is find out based on the weight of hammer and drop of height and the distance in the distance between the impact point and the nearby structure. So if you can see that the bracket in between bracket, this is called the scale energy factor. So when the scale energy factor is more, we can easily say that based on this formula, the peak particle velocity also more. So here is two formula is used based on the scale energy factor. When the scale energy factor is greater than equal to zero point 0.1, we apply the first formula, that is 18 peak particle velocity is equal to 188 into scale energy factor to the power 1.5. If it is less than zero point 0.1, then you use another formula, that is 36 into scale energy factor to the power 0.79. Give me some second. I will join. So sorry for the interruption. So what I discuss here, it is about peak particle velocity. So by scale energy factor, we easily find out the peak particle velocity based on two empirical formula. If the scale energy is greater than factor is greater than zero point 0.1, then we use first one. If it is less than zero point 0.1, we will use second one. So here is one point about the peak particle velocity is given that it is depend on the scale energy factor and geometrical density. That means if the sand is very dense, then it is transferred the energy, very high energy is transferred to the surrounding soil. If it is loose, then the energy transfer is also less. So based and also the if energy factor, scale energy factor, that means uh, height of drop and height of hammer is large, Then also the energy transfer to the surrounding soil is also, and also the distance high, and also if the distance between the impact point and the surrounding structure is less, also the transfer energy is very high. So it is depend on the peak particle velocity is mainly depend on the scale energy factor and geometrical density. The scale energy factor is defined the terms as the applied energy by a single drop and the distance from the point of impact to the point of interaction. As increase the scale energy factor, increase the peak particle velocity. It is clearly seen through this formula. So in the next slide, there is some points about this peak particle velocity. The first one is that scale energy factor is greater than zero point 0.1 for the most rapid impact compaction. The compaction between the comparison between the equation of for two cases show that the rapid impact compaction produce greater peak particle velocity than the deep dynamic compression at the same scale energy factor. That means if we remember in previous lectures that we discussed about the peak particle velocity for deep dynamic compression. So take me some times I can go through it to previous formula. If you remember, it's fine. I think it is. Please wait few minutes, few seconds. I, uh, wait, uh, Here, if you see that the for deep dynamic compaction, for deep dynamic compression, the formula is about scale factor to the power 1.4 multiplied by 70. But in case of rapid impression compaction, this formula is about scale factor to the power 1.53 multiplied by 180. So if the scale factor for both the cases same, then the peak particle velocity generated by the rapid impact stress is larger than or greater than the deep dynamic compaction for same scale factor based on this formula. We can easily say. Then the second for discuss about that the greater the peak particle velocity induced by the rapid impact compaction result from the fact that the steel foot is always in contact with the ground. The greater peak particle velocity transfer to the impact energy to the ground more efficiently. That means if we don't apply the steel plate, the ground surface is quite undulated or not level so much. Though so then if we applying the hammering, the due to this not level proper leveling of the ground, not proper leveling the ground, the applied energy is not uniformly distributed surrounding the ground. If we apply the steel plate and then applying in the hammering, the steel plate is actually distributed the energy uniformly to the ground. So if we the steel plate contacted the ground, the more energy is transferred to the ground. So the test is more efficient if than the other first one when we don't use the steel frame. So it is remembered that it will be remembered that for during this test steel foot is always in contact with the ground. Then its third point it is discussed about the it is compare about the with the deep dynamic compaction. It is said that despite repeat impact compaction produce the greater peak particle velocity than the deep dynamic compression at the same scale factor. The minimum allowable distance to the existing structure for rapid impact compression is typically larger than that for deep dynamic compression because the energy per blow by rapid impact compression is lower. That means it is clear why it is mentioned here like that. It is saying that in deep dynamic compression, we applying energy is high. We apply 10 to 40 tons hammer, and also we, drop of height is about 40 to 40 up to 40 meter or 10 to 40 meter. But in case of rapid injection test, we applied energy is less than the deep dive test because in rapid impact we use 9 to 6 to 9 ton hammer or 15-ton hammer, and drop of height is about 1.2 meter. So applied energy is less. So induced vibration is also less. So we can easily the distance in between the uh, existing structure, existing structure uh, and the impact point is also less, despite the greater peak particle velocity. Because by formula same scale factor, we can see that the rapid impact compaction test generate the more peak particle or greater peak particle velocity than the deep dynamic compression. But in energy terms, the rapid compaction has lower energy than the deep dynamic compression. So you also generate less vibration. So coming to the next slide, one one person LN is reported that the induced vibration frequency ranging from 9 to 15 Hz for rapid impact compaction test. But in case of deep dynamic compression test, it is in between 6 to 10 Hz. So we easily see that due to the induced vibration, the frequency is higher than the deep dynamic compaction in case of rapid induction test. Due to high frequency, we know that less vibration is generated. So we can easily use this test very near to the existing structure to improve the ground. Then one table is given or for different threshold value. It is given by Breaker uh, 2011. It is given for peak particle velocity. What are the maximum peak particle or what are the threshold peak particle velocity for different types of structure, and and what are the minimum allowable distance? We can easily see shown Becker is shown by this table. It is shown that for dry wall, the peak particle velocity should be limited up to 19 mm per second. Remember the unit mm per second. That means it is not greater than 19 mm per second. And also the distance is in minimum distance is in between 14.5 meter. That means the distance should not be less than 14.5 meter for dry well. Like plaster, it is about 13 peak particle velocity not greater than about 13, and the distance minimum distance is not less than about the 19 meter. And other all other structure type of structure, the peak particle velocity is not greater than 51 mm per second and not less than allowable distance is not less than 7.5 meter. Coming to the next slide. Now first we discuss about the uh, design aspect. We're designing the rapid impact test. Now we're applying the into the field. Before applying the field, we apply some field trial test. Whether this test is suitable for that ground aspect or environmental aspect or not, we by trial we determine that. So, in trial, before the full-scale production work, trial test selection section are often needed to determine the optimum grid spacing, number of blows per point, and minimum final set because of the final set for rapid impact compaction test is still relatively new, and because of relatively availability and research result and case history are limited available. That means trial test is needed for this test is because of it is this method is new for us, and there is no such publication for whether it is suitable, what type of what type of soil it is suitable, and whether it is match our targeted value or not. So for that some trial test is go through. So for this trial test, we determine the spacing, number of blows, and minimum set. Then there is one aspect, or there is one criteria is given by Watts and Cooper to before trial this test. That is to select the trial, we need to for area in between 15 meter to 15 meter by 15 meter to 40 meter by 35 meter. That means if we apply the trial, the area should be limited up to 15 meter by 15 meter to the 40 meter by 35 meter. And we apply after applying the one test, we measuring the we find out the SPT value. If it is match our targeted value or it is greater than targeted value, then test is passed. If it is not, then the rapid impact test is not terminated and another type of ground review technique is used. Like that, before the applying conducting this test, few trial are happened. Then here it is said that the resulting degree and depth of improvement are evaluated based on in situ tests such as SPT, CPT by comparing the properties of geometry before and after. We already told that I already told that after trial we conducting the institute test that is common for all, that is SPT test and CPT test. If the value of SPT test before and after we comparing, if the value of SPT test is matching our targeted value or greater than our targeted value, it is fine. If it is not, then we apply some modification is needed. That is, we apply high energy in terms of heavy weight or drop of height. If it is then also if it is not improved, then we apply another type of ground improvement technique. If it is greater than the SPT value is greater than our targeted value, then we all conducting our test. So like this, if we field trial test, we deciding our spacing, number of blows, and minimum final set for rapid impaction test. Coming to the next slide, here it is given different types of design parameters, which is govern the rapid impact test. There is few points are discussed here. One is geometrical type. We know that already in first slide, in first we discussed that this method is suitable for granular material. That means cohesionless soil. It is not suitable for fine grained soil. Why it is not suitable? Because due to the vibration, there is a cohesionless soil. Actually, cohesionless soil has particle to particle friction or extraction is less. So it is when we apply the rapid induction test, it is more suitable for cohesionless soil. But in cohesionless soil, the particle to particle friction or energy or force is more than the cohesionless soil. So due to this applying rapid compaction test, which is not suitable to overcome this particle to particle attraction force. So like that, it is the rapid compaction test is depend on the geometrical types. Then it is in second point, it is written here, it is depth of ground under table also influence the rapid impaction test. In depth of ground, how it is influencing in actually, we know that if the depth of groundwater table is near to the ground surface, there is may some problem. After applying the rapid infusion tank, there may be some water coming out from the ground. They are not easy for to handle the instrument and construction site. So it is also governing factor. To before doing the rapid impact compaction test, we need to dewatering the side. Then also it is influenced by the weight of hammer and also the height of drop. These two are actually directing the applied energy. That means if your weight of hammer and height of drop is high, the applied energy is also high. Also, it is influenced by the diameter of steel. If the diameter of steel flow is very big, so it also uniformly distributed. The energy is very large area. Then also it is influenced by the depth of improvement. That means if it is in between that our targeted depth of improvement is in between 4 to 6 meter, then this rapid impact compression test is very suitable. Then also it is influenced by pattern like and spacing like arc pattern, square pattern, triangular pattern based on the suitability of the ground shape and area accessibility. Then it is also depends on the number of blows. If number of blows is high, then the impact energy also high, applied energy also high, more energy will transfer to the ground. It is also governing. Then the distance to the existing structure or utility lines. That means if the we know that the rapid impact compression test is generating the less vibration, so we can easily use this test very near to the existing structure. So it is also a governing factor. Coming to the next slide, we use here it is see that design procedure. So step by step, first we define the design consideration, designing the what are the different number of blows, the spacing. After that, we conducting the trial. Then now we apply the procedure, how we apply, discussing the procedure how we apply in the actual field or actual ground. So here it is said that first procedure is to determine whether the rapid infection is suitable for me. How it is determined if our depth of improvement is in between 4 to 6 meter, then we go to this rapid improvement and the geometrical type is suitable in granular soil or questionless soil, then we apply this test. Then we select the depth of improvement. How much depth we needed, whether it is 6 meter, whether it is 4 meter. If it is 6 meter, then applying energy is more applying energy is required. If it is 4 meter, less applied energy is required as compared to the 6 meter depth of improvement. Then we determine the applied energy based on this formula and also based on some relationship given in tabular form given in this slide. Then we select the spacing pattern which is suitable, whether it is suitable for arc pattern, whether it is suitable for square like that. Then we determine the number of blows based on this formula again, and we decide the pattern and like that. In next slide, it is said that after determining the number of blows, we actually safety purpose we actually determine the peak particle velocity. By this by scale energy factor, whether the peak particle velocity is exceeded our targeted value or not. If it is exceeded our targeted value, then the rapid induction test is terminated. That is, no further test is needed or conducted to improve the ground. We know that peak particle velocity indirectly show the environmental impact. So we already show one table that based on the peak particle velocity, for different structure, there is some threshold value is fixed. If it is exceeds this threshold value, we terminated this test. If it is in between or less than this peak particle velocity, which is already given in this table for different type of structure, then we conducted the further test to improve the ground, further rapid impression test to improve the ground. So here we can see the same formula is given for peak particle velocity and same table is given once again. We see that if it is exceeding the 19 mm for dry well, per second peak particle velocity is 19 mm per second for dry well, then the test is rejected for this particular site. If it is less than 19 mm per second, then it is go for the test for other test, or for rapid impact to improve the ground further. So like the different type of structure, different type of threshold value is given for peak particle velocity, and also different types of different distance are given, minimum distance are given, how much the distance, minimum distance should be there to be in between impact point and nearby structure. So now in this way, module 4 lecture 17 is completed. Now we can take 5 minute break. After that, we continue the solve the continue our session and try to solve one problem based on the rapid impulse. So please stay on the line and meeting. Don't leave. I will join after 5 minutes. Then we complete our session and also discussing another technique, that is vibro compaction method. So now we take some 5 minutes break. Please stay on the line. I will join after 5 minutes. So, welcome back to our session. Now we discuss here about one problem about the rapid impact compaction test. Here it is. Uh, Here one problem is given that is said that a newly reclaimed site with 4-meter thick field, mostly silt sand with SPT number and is equal to 6 needs to be improved to an SPT number 40 for a construction project. The groundwater table is at 1.5-meter depth. A contractor has a rapid impact compaction with hammer weight of 9 tons and drop of height of 1.2 meter. The energy requirement for improving the 4-meter thick silt is sent by rapid impact method is 190 ton per meter, 1 meter per meter square. Provide a preliminary design, pacing, number of blows by rapid impact compaction. Verify the environmental condition if a warehouse is located at a distance of 7.5 meter from the site. To try to solve this problem, I directed you another slide. First, you see that the applied energy is the geometry or targeted geometry is our silty sand. And for silty sand, impact energy is given by 190 ton meter per meter square. But our depth of improvement is 4 meter. But one table is given for silty sand is applied energy when we apply when we hammering or apply the rapid impact compaction, the applied energy for 190, the depth of improvement is 4 meter. But here it is given, depth of improvement is 3 meter. But here it is given 4 meter. So more energy is required as compared to given energy. So how it is find? Now we directed to the another slide. We find this by unitary method. That means for 3 meter, depth applied energy is 190. Like that for 1 meter, how much it is, and for 4 meter, what is this? It is find that for 4 meter, it is find out about 253 ton meter per square. And we consider that our pacing is 1.5 meter by 1.5 meter. That means for one one impact point to another impact point, the distance is about center to center distance is about 1.5 meter. So by this spacing, we consider square pattern. So by this spacing, we easily find out the influence area. That means nothing but it is a square of spacing. So you can easily find out. And after that, this influence area, we easily find out the number of drop by this formula. It is rearrangement, this type of formula, that is applied energy is equal to number of drop into weight of hammer into drop height whole divided by influence area AE. So by rearrangement this formula we can easily find out the number of drop. Here it is find out that number of drop is about 53 numbers for each impact point. Then we find out this formula for considering the environmental impact, whether this test or given problem is suitable for our existing structure or not. Here it is, if you see that the existing structure is near about 7.5 meter distance. So by this distance and by this applied energy, we can easily find out, we can easily find out from this formula our peak particle velocity, which is indirectly given the environmental impact by through vibration and noise. So we know that for all other types of structure, the peak particle velocity should be limited to 51 mm per second. But in our case, it is by this formula we find out about 53.2 meter, which is slightly greater than the threshold value. That means for this test, for this type of problem, we cannot apply the rapid impact test for this type of existing energy, so existing structure. For this, we need to limit our impact peak particle velocity. How it is limited by increasing the distance. That means impact to distance between the impact point and nearby structure. If we increase, then the peak particle velocity decrease. So by increasing the distance, we easily reduce our peak particle velocity, and also we conduct or rearrangement our impact point. So like that, we by small adjustment we apply the this test in our field. Sorry about that. So coming to sorry for sorry, I cannot find my yes. Hey, close over there. Okay. Okay, sorry for that. Actually, mistakenly I deleted or closed the tab. So now coming to the next slide, it is about the construction. That means how we apply the rapid impact test in the ground. So first step is we do the design, then we do the trial, and after that we now in how it is actually apply in the field we now discuss. So for construction of the rapid impaction test or rapid impaction, we for prior to the compaction or stabilization, we need to prepare the ground. How it is? By removing the large object, leveling the ground, dewatering, or filling the existing pond and depressed area like that. Dewatering to lower the ground level water if the groundwater is within the 1 meter. That means if the groundwater is very close to the ground, is about 1 meter, then we need to dewater the ground. Then leveling the site to avoid the ponding of water, removal of large debris or rubble uncover if any during leveling to avoid the interference in compaction work. Then in second point, we will discuss about the to build the isolation trench when it is to build when our the vibration is very large, that means the impact due to the rapid impact mobilization, the if our vibration is quite large or the peak particle velocity is quite large, to reduce that or to transfer to the existing structure, to reduce to minimize to transfer the existing structure, what trench is created surrounding the test site. The to the main purpose is to build the trenches. Trench is that if due to this trench, the further transfer of vibration is not possible due to there is gap. So one trenches is built and the trench should be 1 meter deep, sorry, 2 to 3 meter deep and 1 meter wide. So in between or surrounding the existing structure to reduce the vibration. Then we decide the impact point, whether we go for a layout or whether it is square or arc. Based on that, we point out in the ground and then started our test. And then we apply the steel foot or steel plate and then applying the hammer. After each test or each impact point, after applying the rapid inspection, improve mobilization or ground improvement technique. After each of the point, we need to find out the number of blows and minimum final set, whether it is our match our targeted value or not. After each of the impact point, then we re-leveling the work area and re-establish the survey point for the next part. Then, if the area are found to be extremely hard or soft, we actually excavate it and replace the granular seed. After that, in the final pass, level all the craters and apply the surface compaction by vibratory roller and take the final survey to estimate the settlement after the compaction. Like this way, we apply the rapid impact compaction in the real field. So coming to the next slide, it is about the quality control. During the rapid impression test, we need to check the control or need to check the quality or control the quality. By this, we apply one. It is performed actually one data acquisition system, which is already attached or built in the equipment or excavator. So data acquisition system actually what happened? It is recorded the number of blows, total energy, vertical displacement, and total depth of penetration. And also by these values, we actually monitor our test in one point. If it is match our targeted value, we move another point. If it is not, further improvement is needed. Like that, we control the quality in the site. In the second slide, it is another aspect is quality assurance. Quality assurance is that we assure, that means we after each test or after each pass or after each rapid uh, infection ground improvement technique, we go to some institute test like SPT test or CPT test. Before also we go for SPT test, CPT test to measure the ground strength, and after also that, uh, and then match our targeted value. If it is matched, then the test is okay. If it is not matched, further improvement is needed. Like that, we use SPT, CPT, and test to improve or assure the quality about the rapid inspection test. So this module is over. For now, we start about the module 5, vibrocompaction. In vibrocompaction, this is another type of ground improvement technique. This also a deep ground improvement technique. So like rapid impaction, deep dynamic compaction, shallow compaction, these tests are quite similar, and it is limited up to a certain depth, up to 15 meter. Like deep dynamic compression is up to 15 meter, and rapid impact compression test is up to 4 to 6 meter. But in vibrocompaction test, we densify the soil or depth of improvement is about 40 meter. Mostly is about 20 meter, but we can go up to 40 meter to densify the soil. So it is quite popular to densify the soil for greater depth. So it is more effective than the other types of ground improvement technique, which we already discussed in this session. So starting with that, some basic concept about the vibrocompaction is that In vibrocompaction, we drive the vibrating probe into the ground. Like one rod is driven, a probe is driven to the ground during vibration, and then we apply the vibratory force to rearrangement the particle to denser state. Actually, what happened in vibrocompaction, we overcome the particle to particle uh, 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 friction force. That means the bond between the particles we overcome by the vibration. Due to this vibration, particle to particle interaction is broken, and the particle is come more closer like previous. So then previous, then but it and this test is more suitable for saturated cohesionless geometry. In saturated cohesionless geometry, vibration causes development of excess pore pressure. Due to this excess pore pressure, liquefaction is generated. Due to this liquefaction, the interparticular contact force is reduced, result in the reduction of interparticular friction, that is unlike shear force or shear strength, and also the particle are rearrangement and come become very closer, come compact to very closer. In dry cohesionless soil, water is injected to compact to make the compaction easier. Due to this water, excess pore pressure is generated and liquefaction is generated. So it is quite easier to particle broken the particle to particle friction. So easy to compact the ground. Moving to the second slide, it is said that the backfill is often used to improve the degree of vibrocompaction. This technique, also called the vibroflotation. Backfill is needed because when we apply the vibration or vibrocompaction, there is some subsidence or void space are created because particle previously particle are arrangement in between interparticle bond, but we broken the bond and particle are more closer than the previous, and there is some gap or void or volume are reduced, and there is created some void or subsidence. So to for that we backfill some good material to fill this void and again apply this vibroflotation or vibrotest. This technique also called the vibroflotation test and first developed in Germany in 1930 and then successful for worldwide and quite popular also. So vibroflotation, nothing but the vibrocompression we can say. So we apply this vibroflotation or vibrocompression in two ways. One is bottom vibrator, another one is top vibrator. In bottom vibrator, we actually the vibrator is attached to the at the bottom of the probe. So that's why it is called the bottom vibrator. In bottom vibrator, the vibration is occurred by rotation of an eccentric weight at the bottom of the probe. And on the other hand, in the top vibrator, the vibrator is attached at the top of the probe, and most of the uh, then apply the vibration in the ground in the similar manner, like inserting one rotation of an eccentric weight to create the vibration. Moving to the next slide, here one schematic diagram is given for vibro compaction. So it is shown that one first we apply the insert the vibrating probe into the ground. After a certain date, we apply the vibration, and there are some voids or volume or decreases, and we apply the backfill material, and then again we apply vibration, and like that we raise our up to ground level, and we improve the ground. That's why we by this way we apply the vibro compaction. We also call it is vibro flotation or vibro flow. Then come to suitability. Vibro compaction is suitable for densifying the deep deposit of questionless geometry up to a fine content 20%, but less than 3 to 4% clay particle. That means this technique is mostly suitable for questionless soil with less fine contents and also less than or very less than clay particles also. Because if fine contents uh, uh, reduce the void space so in between or if in vibrocompaction, portionless soil, when we apply saturated portionless soil, vibrocompaction, we generated the uh, excess pore water pressure. Due to this excess pore water pressure, liquefaction is happening. Due to this liquefaction, interparticular bond or friction is reduced and particle come very closer. But in case of fine if there is presence of more number of contents of particles, then the permeability is reduced and the excess pore water pressure is easily dissipated. So there is some problem when there is some problem when happen when it is present of clay particle. So it is more suitable for questionless soil with less clay particles. That is about 2 to 3%. So one scientist, Saito or researcher give one chart about the or graph about the percentage of fine based on the SVT number. Here it is SVT number we apply to indicate the depth of improvement. More the SVT number, more depth of improvement or more improvement is happening. So one chart is or graph is given in the next slide. So you can see that it is SPT versus fine contest. Before the improvement, the SPT value is quite similar for all type of fine content. After that, when we depth of after the vibro compaction, we can see that the SPT number is increasing, like 20 to 30. Yeah, 20 to 30. SPT number is about 20 to 30 increase for less fine content. You can see that here the SPT number is about 30, but the fine content is about 3 to 4%. If we increasing the fine content, we can see that the SPT number is decreasing. That means the ground is uh, improve the depth of improvement or ground is improvement is decreasing. So we easily say that the fine content affect our improvement. So in this test, the vibrocompaction fine content should be limited. It is less than 10% and clay particles should be less than 2 to 3%. So if less, then SPT number is low. That is more depth of improvement. So coming to the next slide, here it was chart is given for suitability of the vibrocompaction. This chart is nothing but the gradation chart. It is this gradation chart is divided some zone A, zone B, zone C, and zone D based on the particle size. In zone A, it is about the gravel, mostly about the gravel particles. In zone B is from gravel, fine gravel to coarser sand. In zone C, it is in between the coarse sand to fine sand, and zone D is in between the silt. So it is here. It is show that the zone A vibrocompaction is appropriate, but penetration is difficult. Zone B most suitable for vibrocompaction appropriate, but zone C vibrocompaction is feasible but no longer required. Zone D vibrocompaction not feasible. Use stone column. We suggest here to use stone column, not feasible. So why it is happened in the coming slide we discuss. So here it is said that the vibro compression is most suitable for zone B because in zone B most of the particles are is cohesionless particle or cohesionless soil type is most of the cohesionless in between fine gravel to fine sand or sometimes coarse sand. So particle to particle friction is only to break here. No need to overcome the cohesion. So less cohesion, less so more easy to apply this vibro test in between zone B. In zone A, it is not feasible because of the large particle is present. Due to the large size of particle, that is like gravel, pebble, like that, or cobalt. So the penetration is difficult. So due to this difficulty in penetration, it is not suitable in zone A also. But sometimes it is feasible like that. In zone C, it is also maybe feasible, but require longer time to densify due to the apparent cohesion for unsaturated soil and low permeability for saturated soil. So this also zone C also not fully suitable. Only zone B is suitable because of this gradation in between the gravel and fine sand. But in zone 4 it is not suitable because the fineness and plasticity reduce the effectiveness of vibro compaction. So zone D also not suitable. Zone D is even not suitable. Even this means like zone A and zone C, we apply this test in some extent, but in zone D we do not apply this test because here we need to uh, deal with the fineness and also deal with the plasticity, which is reduce the effectiveness of the vibro compaction. So this technique works well for saturated loose question-like geometry. We already discussed why it is, and if the dry geometry is encountered, flushing water may be used to host site even to ease the vibro compaction. Because if water is present in portionless soil, the excess pore pressure is developed and easily liquefaction is developed and easily overcome the interparticular forces. Then come to next point is vibrocompensation method is has been used to densify loose crystal up to 40 meter, mostly 20 meter. This is also already discussed here. Coming to the next slide, it is about the application or applicability of the this technique. It is like other ground improve technique. It is also improve the or increase the bearing capacity, reduce settlement, mitigate the liquefaction for wide variety of project and like that. But this technique is used for loose questionless soil or saturated soil. Then there is given some projects whether it is mostly applicable, like storage tank, buildings, roadway, dams, and dikes. And this technique is most suitable and rapidly used. And this all these techniques are big project. That means cost of this project or construction is required more. And also risks of this to build these techniques is require more risks. So to stabilize this rate happen disaster big disaster is happen if this ground is not stabilized for this. So this technique is required technique is applied this much of big project only or most cost of construction is very high and also the risk associated with this project is also very high. Coming to that, had discussed about the advantage and disadvantage. So we have already discussed this. This technique is very quick, easy, and economical. quick in the sense only one probe is driven to the ground and vibration is generated, and due to this vibration soil is densified, and like that we raise the up to raise the probe and again vibrate it, and like that we come to the ground surface, and like we very quickly we densify the ground. And easy also, only one probe, vibrating probe is required to densify that, and can be used to improve the geometry above or below groundwater. See, we discussed about the shallow compaction, deep dynamic compaction, and rapid impact compaction. All the three are not suitable when the groundwater table is near to the surface. But in this case, it is not happening. It is suitable both the case when the groundwater table is below or above for a certain level. So these are these uh, advantages. Now disadvantages is that it is only used to the questionless geometry with a clay content less than 3%. That means it is not used for clay soil, silty soil. It is only for the questionless soil. And so all other another type of geometry we use another type of groundable technique. But this technique is most suitable for questionless soil. It is one of the disadvantages. Then another disadvantage is that installation induce vibration and possible ground sustain. That means due to the poor vibration, the surrounding soil are vibrated. Due to this vibration generated, the existing structure, nearby structure also vibrated and may get damaged due to this vibration. So one damage is one setback, or we can say one disadvantage is there. Also, it possible ground accident. Due to this vibration, particle to particle interaction is inter friction is overcome, and particle is come very closer very quickly. So suddenly there is subsidence, ground subsidence is happened. So this may cause the hazard in the surrounding area. That means suddenly the surrounding area is suddenly collapse due to this vibration. So this type of disadvantage or this type of risk is associated with this test. Coming to the next slide, we discuss about the principle of the, or we can say the mechanism of the vibrocompletion. So it is said that the densification of questionless soil results from the particle rearrangement and volume change by the induced vibratory force. And vibrocompletion induces the lateral vibration and vibratory force. The induced vib force should be larger than the interparticle friction. For rearrangement of particles, the force attenuated with the increase of distance from the compaction point. Here it is clearly said that the questionless granular soil or questionless soil, when we apply vibration, the vibratory force is generated. Due to vibratory force, interparticular friction is reduced or overcome, and the interparticular friction is overcome, and particle rearrangement particle has happened, and the particle very come very closer, and ground is compacted. So one scientist, Roger, reported that a critical acceleration of approximately zero point 0.5 g is created, above which the dynamic stress is induced by dynamic compaction, destroy the structure granular soil. That means minimum zero point 0.5 g acceleration is generated to apply the vibrocompaction test. And when the acceleration is increased to more than 1.5 g, the shear strength of the soil is significantly reduced and the soil is fluidized. And the particle to particle friction is uh, broken, and easily, quite easily, the soil is come closer. And further increase the acceleration, that means nothing but vibration, exceeding the 0.3 g causes soil dilation. Like that, in each vibro float compaction point, this This is happening. Now we discussing the points, how it is happening, and idealize the response from the question is soil around the vibratory fluid, and how it is happening near the structure, near the vibratory fluid. In one proof point or in one impact point by vibratory fluid, four zone is created based on the acceleration or based on the uh, compaction or compactive force. So this zone is depend on the distance. It is depend on the distance, and also based on this zone, soil desiccation is happening. If we say that we apply the vibration force is here, probe is here, the vibration is generated. So this area one is has larger vibration than the area 2, 3, 4. That means this area is associated with point 3, or we can say that 3G. Acceleration is about 3G, 3.0 G. In the previous slide, we also discussed 3.3 G. Meaning acceleration is quite high. That means vibration is quite high. So is the in this zone dilation is happening. So from this zone, when the acceleration is uh, greater than 0.3 G, dilation is happened. Dilatory or dilatory zone is created. That means particle is like fluid like that. Then when the acceleration in between point further moving to the next area, area 2, the distance from is quite large distance from this point, but smaller than the 3 and 4. Another zone is created fluid zone, and the acceleration in between 3 to 1.5 G. So this zone is called as fluidized zone. And then further, when the acceleration is between 1.5G to 0.5G, then another zone is created, that is compaction zone. And when the acceleration is less than 0.5G, last zone is created, which is called the elastic zone. This zone actually depend on the distance. When the distance is very close to the vibratory flow, zone 1 and zone 2 is created. That is, dilatory zone and fluid zone is created. When distance is increasing, the influence also reducing, then zone 3 and 4 is created. That is, compaction zone and elastic zone is created. So so best is suited this test when the in between the zone 2 and zone 3, the border in the best suited this test. That is, in between the fluid zone and compaction zone, this test is best suited. Now discussing one by one these two. So there we already discussed that there is four zone. One is dilatory zone, fluid zone, and then fluid compaction and elastic zone. In fluid zone, soil in dry soil, dry state soil losing the stability. But in saturated soil, liquefaction is happened at a high acceleration. So like that, when vibration is happening and with quite high acceleration, the soil becomes fluidized. And due to this fluidization, liquefaction is happening for saturated soil, and for dry soil, soil loses stability. And by this two way, soil intergranular particle force is reduced and soil is come closer. And then another point is that the material in the dilatory and fluidized zone are in plastic state, while those in the compaction zone are is in an elastic plastic state. That means fluid zone is associated with or fluid or dilatory zone is associated with the plastic stain. That means stain is at constant strength, stain is continuously increasing. No further increase in the strength. And the compaction zone is related to the elastic plastic zone. Elastic plastic zone like that, increasing the graph. After the certain point, it has become plastic. So the compaction zone is related to the elastoplastic zone. This test is best suited when at the boundary between the plastic zone and compaction zone. The compaction zone is extended to the point where the no further densification is happened. This is called elastic zone. That means if we increasing the distance from the impact point, the influence zone is also reduced, and the state of soil is also changing. First is it is dilatory and fluidized zone, which is nothing but plastic zone is happening. Then happening compaction zone, which is nothing but the elastoplastic zone is happening. Then it is happening whether the no infection or no influences happen. This is called nothing but elastic zone, which is normal state of soil. Moving to the next slide, it is discussed about the deep versus surface compaction. That means when we apply the vibro compression in deep and when we apply the vibro compression in surface, which is more suitable and why? It is said that simulating deep compression by horizontally rotating vibrator at a depth and the surface compression by a vertically oscillating vibratory numerically, it is shown that the deep compression has a wider radial influence distance than the surface compression. And this test is numerically shown by Arnold and Herman in 2009. That means it is clearly said that by their test research that the deep vibro is more suitable or more densified or more influence area than the surface compression. The deep dynamic compression also generates a more uniform volume change than the shallow compression. It is also one advantage the deep dynamic compression, deep fiber compression. So why it is happening? It is happening because the deep compression attributed the better performance to multi-direction sharing mode induced by the combined vertical and rotational movement of vibrator. That means when we apply the deep compression, we apply multi-directional sharing mode. That means we apply vertical load, also we apply horizontal load, also we apply the rotational movement of the vibrator. So, but in surface we cannot apply that. So the depth of improvement also not suitable for surface compression, which is suitable for deep vibro-compaction. In the next slide, it is show compare the in two graphs to compare the deep vibration and surface vibration. It is clearly shown for different cycle. It is clearly shown that the graph is based on the void ratio versus distance. It is clearly shown that when we increase the cycle, number of cycle or number of vibration, increase the vibration in terms of cycle, the depth of improvement or in terms of void ratio, that means void ratio decrease is also higher than the when we increase the number of cycle. And also we can see that influence area is also higher. That means from here to here, the influence area. That means about 1 to 4 meter. Our influences for deep vibration. But in case of surface vibration, we see that the void ratio reduced void ratio is less. That is, void ratio is reduced very less in surface vibration, and also the influence area or distance is also less. It's about 0.5 to 1 meter only. So this test, by this clearly numerically, it is shown that this test is not suitable, is less suitable for surface vibration, but is greatly suitable for deep vibration. So why it is happening? Now I discuss. So installation process is that to minimize the post-stuff resistance, penetration and extraction of probe to be done at high frequency. Masters and Felonius suggest a frequency higher than 30 Hz penetration for penetration and extraction. At a higher frequency, it causes the low ground vibration and less energy is transferred to the surrounding soil, causing the penetration and extraction easier. During the compaction stage, the preferable frequency is close to the resonance, resonance of the geometrical mass so that more energy is transferred to the surrounding geometry to make the compaction efficient. Also, during this process, penetration probe is also slow. Typically, frequency of resonance of the soil is around 15 to 30. So in this slide is discussed that when we applying the or inserting the probe, we applying the high frequency. Due to high frequency, less vibration is generated. Because of less vibration, the ground, the friction, we overcome the friction to this surrounding soil, influence and not disturbing the influence area of this surface, and we easily insert at a depth, quite deep depth. And due to the and also the energy transfer is also less at the high frequency because it is at the surface the interparticle to particle bonding is very low. So due to this vibration, low high frequency vibration is not transferred to the surrounding soil and less energy is transferred. But when we reach our targeted point or targeted depth, we reduce our frequency and reduce to up to soil fundamental frequency. Why we reduce to our frequency to match the soil fundamental frequency? We actually one phenomena is happen resonance. We match this phenomena. We happening this resonance. Actually, what happened when the soil frequency matches with the vibration frequency, suddenly the amplification of the surrounding soil or amplification of the disturbing of the surrounding soil is increasing with same amount of energy. So by this resonance, we easily uh, we apply our densification technique with small amount of energy also. So when our target is that when we inserting the probe, we apply high frequency like 30 hertz. But when we after reaching that point, we apply the frequency to match the soil frequency, which is less than the 30 hertz or is also in between 15 to 20 hertz. It is given by Marces and Fellinius. So when the soil frequency resonance happens, due to the resonance, suddenly the disturbance is quite large, and due to this disturbance, easily at same energy, easily we overcome the interparticle friction force and soil get densified. Coming to the next slide, it is show the about the one schematic diagram about the insertion of the insertion of the vibratory hole. So it said by this graph, it is said that for first we apply a 30 hertz high frequency. We apply insert our probe, and at that point we go to the frequency at 30 to 15 to that is matched to the soil frequency at 15 to 20 hertz, and compacting in this here, and after compacting we lifting the probe up to that much depth, During lifting, we also applying the or extraction. We also applying the high frequency. After that point, and then after also extraction, instruction also happening the high frequency, and that we reach that point with low frequency and compacting the soil to match the resonance of the surrounding soil. And like that, we extracting, and reach the ground surface. And below this ground surface, we compact surrounding, compact the ground and achieve our targeted value or densify the soil. So coming to the next slide, it is one graph is show that in between the degree of influence and the distance of the compaction point. This degree of influence mainly depend on the two point. One is compaction energy, another one is time. This graph it is clearly showed that when we increasing the distance, the influence zone also reducing. That is degree of influence also reducing. That means our impact point is here. So degree of influence is like that, like that, like that. So after increasing the distance, influence degree of influence is also reducing. That means the energy is required to here is higher than from here. So also reducing the degree of influence. And if we increase the compaction energy, our degree of influence also increasing because more vibration is generated, more particle are more surrounding particle are come closer, but it is reducing to increase the fines. That means if the fine content is increasing, our degree of influence also reducing because the fine content increase the reduce the permeability. So particle or increase the apparent cohesion. So particle to particle bond is increasing while the fine contents are present. So degree of influence is reduced. So one scientist it is showed that the influence Mitchell showed that the influence radius decreased from approximately 1.8 meter for clean sand to 0.6 to 0.9 meter for sand with more than 20% fines. So by this test, Mitchell he showed that fine contents govern the our degree of influence. For thin sand, it is 1.8 meter. That means degree of influence is about 1.8 meter radius. But in case of it is reduced up to zero point 0.6 to 9 meter when there is fine content is greater than 25%. So by that we easily show that we easily conclude that degree of influence is governed by two factors. One is compaction energy and another one is distance to the compaction energy. So now we conclude our session here. So here we are now we stop. Already it is 8:05. We will now stop here. You don't know. I will send the what are the discuss here or the materials I discuss here. I am sharing to the Nptel team through Google Drive, and also the mm, video is recorded. So the video also shared to you through YouTube link, and we in Google Drive I also shared the week 4 assignment 2021 solve problem, how it is one by one we solve the problem. Week 4 assignment 2021 problem only, not present here. and I share to everyone. And also, I will share uh, one problem regarding the rapid impression test, and also share some few material about the Bible compassion regarding the upcoming lectures. So please go through it, and thank you for all to attend our session. And once again, very I wish you very happy weekend. And this session will be already will be shared to you. Don't worry, and like the now I closing here. So we leave the meeting here, and we will join in the next session in week 5 lectures. And be happy, and thank you for all. And now I closing my session. So thank you. We will meet once again in the next upcoming week. So thank you.